네, 송희경 교수님 시작해 주시면 감사하겠습니다.
네, 감사합니다. 영어로 발표하도록 하겠습니다.
네, 알겠습니다.
Thank you very much. Good morning, everyone. I'm Ickhyun and I'm currently an assistant professor at the Department of Electronic Engineering at Hanyang University. And the title of today's talk is Device and Circuit Optimization for Extreme Environment Applications. And this is the outline of my talk. So first, I'll talk about the brief introduction to myself and my research background, followed by radiation effects and cryogenic operation. And then I'll talk about my current research. Then I'll summarize my talk. So this is one-page introduction to myself. So it's in chronological order. And the main research theme throughout my research career is the performance optimization of electronics with holistic approaches. And during my master's and bachelor's years, I worked on the thermal noise modeling of CMOS transistors and CMOS low noise amplifier optimization. And then at Samsung Electronics, I work on the design of read and write paths of next generation phase change memory. And at Georgia Tech, I worked on wideband radio frequency circuits along with the radiation effects on the electronics. And at Oklahoma State University and Hanyang University, I basically extend my previous research topics. So it includes RF device and circuits and extreme environment electronics as well. And I also work on following these related topics. Okay, so let me talk about the extreme environment electronics. So we can categorize our electronics in two types of electronics. The left side is our electronics for daily use. And on the right side is for some special use. And if you compare these two types of electronic systems, there's a big difference. So this figure is Chinese space station called Tiangong-1, which was launched in 2011, and it conducted some various space missions in space. And its functionality is it has stopped in 2016. And if you guess the development cost of this system is tremendous. It's about 2 billion US dollars. But surprisingly, the initial target lifetime of this system was only 2 years. So if you think about the resource invested for implementing this system, which was about $2 billion, but you expect its lifetime is only about 2 years in your design phase. So this is somewhat very inefficient way of building electronic system. So we want to know what makes this difference. So for a typical cell phone and car electronics, we can use more than 5 years, and maybe you can use 10 years for vehicles. So we want to know the differences between these two types. So that leads to us the operation in extreme environment. So extreme environment simply means the operation under harsh conditions. So that could include wide temperature range, which could be very, very low or very hot. In addition to that, we expect intense radiation effects. So this impose significant differences between daily electronics and electronics in the extreme environment. So application-wise, you can think about space-based systems for various types of applications. You can think of satellites, of course, and CubeSat network, and potential space missions to the moon or Mars in the future, in the near future, right? And in these systems, we also need very high precision operations that controls accurate motion, including proportion or positioning, and sometimes it needs to support real-time operation. And in terms of performance metrics, we need very good data rate, gain, and low noise performance. However, we have some restrictions. We cannot violate these stringent requirements. So in order to design this kind of systems, device circuit optimization is critical to achieve target performance. And this topic have been actively investigated by government labs, relevant industries, and academia. So let's talk about the radiation effects. There are three main radiation mechanisms, and the first one is the total ionizing dose, which is called TID, and it's over time degradation due to charged particle or proton, and the device will get traps in the oxide and interface regions, and that leads to increase in leakage current and a shift in the threshold voltage. The second one is displacement damage. So that's from the collision with neutral and charged particles, and the device structure or lattice structure has some defects. So it could lead to carrier mobility decrease and transistor or circuit gain reduction. The last one is the single event effect, and it's a little bit different from these two mechanisms because it's dynamic phenomena. So when your electronics or transistors hit with the high energy particles, the current or voltage transient will appear at the device terminals as shown in this figure. So if heavy ion hits your device, and then each terminal will generate its corresponding transient in terms of voltage or current. And that will lead to data loss or interference, and there will be corruption in signal integrity. So in order to minimize single event effects, it's critically important to minimize transient peak and duration in the design phase. So I focus on this mechanism in this talk, and I briefly touch the other ones. For the previous research, people widely use TMR technique, triple modular redundancy. So it's simple. So you basically have three identical circuits to generate output, and the final output is determined by the vocal logic. So if any of these two modules have the same output, for example 1, 1, 0, then we take 1 as the correct output. And we also have some layout techniques, so you could modify the well area or sensitive node, but most of these techniques are effective in designing digital circuits. On the other hand, relatively few ideas have been suggested for analog or radio frequency circuits. So my research target was to investigate the design techniques to reduce single event effects, and that idea should be verified in both device and circuit level. So this is the my research focus. So I mainly use silicon germanium heterojunction bipolar transistor technology for operating under radiation condition. And silicon germanium HDT exhibit high performance in comparison with the CMOS technology or other 3-5 technologies. And it shows acceptable tolerance to total ionizing dose and displacement damage as well. However, it exhibits high susceptibility to single event effects. So we need device and circuit optimization technique to minimize the single event effects in the analog or RF circuits. So my research focus has three subtopics. So first one is the investigation of mitigation techniques for single event effects. And we need to verify the performance and explore the trade-off in design space. And I also worked on the total ionizing dose and cryogenic operation. So this is the first topic about radiation effects. And here I will talk about the single event effect mitigation approach, which is the inverse mode silicon germanium HBT. So as an introduction, the silicon germanium BiCMOS technology has some sort of bipolar transistors, as you can expect, but in comparison with the silicon BJT, it has graded germanium layer in the base area of the transistor. And by bandgap engineering, the current gain or unity gain frequency, only voltage, noise performance have been improved. And it also integrated with CMOS transistors, as is shown in this figure. So you have PMOS, NMOS, and silicon germanium HBTs on the same chip. So you can use CMOS libraries for building your system. And this is the high frequency performance over technology generations. So these days, fifth generation SiGe HBTs, which is about 500 FT and 500 gigahertz of FT and Fmax. So if you recall the bipolar transistors in our textbooks, you probably remember the forward active region, because in this region we can get large gain, large output impedance, large breakdown voltage. So our design and optimization is mainly based on the forward active operation. On the other hand, we do not talk a lot about the opposite quadrant for BJT, which is reverse active region. In comparison with the forward active operation, it has smaller gain and smaller output resistance. So we don't want to use this region for designing some circuits. But reverse active region or inverse mode has some unique advantage. And inverse mode is simply the emitter up and collector down topology. So you can simply swap the device electrical connections like this. So emitter has higher voltage potentials and collector has lower voltage potential. And the benefit of using inverse mode is that it's less sensitive to single event effect, which means it has less transient peak and short duration and smaller charge collection. So this is a detailed model and the simulation of the single event effect. So from this, we can compare the forward mode and inverse mode of response to the single event effect. As you see, we see that the peak reduction and duration reduction as well, along with the integration or charge collection. So the reason we get better single event effect is that the excess carriers generated from this subcollector substrate region has barriers implemented in the device structure itself. And that means smaller number of excess carriers effectively reach to device terminals. And internally, the field between the emitter and base is much greater than the base to collector. So higher electric field will sweep the excess carrier much faster than the forward mode operation. So as you know, the inverse mode or reverse active region will give relatively poor performance, but as technology scales, the performance of inverse mode operation has improved significantly. So for different generations, we see that current gain or beta is now about more than 200. and the FT has improved to more than 20 gigahertz. And if we have some options to modify the design kit cell layout, then we can actually improve the FT more than 30 gigahertz. This is from the 90 nanometer or 130 nanometer technology node. So these improvement implies that inverse mode could be applied to higher frequency circuit design in order to minimize or mitigate the single event effects for circuits or systems. So here we applied inverse mode silicon germanium HBT in radio frequency low noise amplifier. So for typical low noise amplifier, we use a cascode configuration for various benefits. And if you think about applying inverse mode operation to cascode configuration, there will be 4 combinations. But if you think about the performance of the circuit, the bottom transistor will have the dominant effect in determining the circuit's performance. So we don't want to significantly hurt the RF low noise amplifier's noise or gain. But for the common base transistor, their primary job is to do a current buffer. So its impact on the overall performance is much less dominant. So we can apply the inverse mode operation to the upper transistor or common base transistor. The corresponding LNA schematic will be like this. So you have some matching network, and for cascode configuration, you use inverse mode for upper transistor or Q2. So we build the circuit and we use GlobalFoundries 130 nanometers silicon germanium BiCMOS platform. And if you see this performance summary table, there is very little difference in terms of gain or noise figure or linearity of the circuit, which means if we apply inverse mode to reduce the single event effect, it does not degrade the circuit's RF performance, and while we expect the better single event effect sensitivity. So we built a TCAD, technology CAD transistor model and calibrate against the design kit or measurement result. So this is the Gommel plot of the TCAD model. And from this model, we can simulate the single event effect response. So when single event effect happens at the lower transistor, we see peak reduction. And if the single event effect happens at the upper transistor, we see peak reduction and duration reduction as well. Here we saw some conversion issues, but sometimes it's very difficult to get very clean TCAD response. But at least trend-wise, we expect the improvement in the single event effect sensitivity. So for the experiment, we used first laser 2-photon absorption technique. So here we basically use a laser to mimic the heavy ion collision. And depending on the energy level, we can get deterministic transient response. And another benefit of using this technique is we can fine control the focal point. So you can adjust the depth or position of the laser so that you can directly hit your active device. And the result has strong correlation with standard heavy ion testing, which is very expensive and which takes very long. But we can get correlated result using this much simpler experiment setup. So your laser hits to the backside of your chip, and you can find the location of your transistor and it will generate the corresponding transient. And this is the photo of the measurement setup. So from the experiment, here we have 2D raster scan. So these bright shades are matched to each transistor in the cascode configuration, and the color is mapped to the magnitude of transient, peak magnitude of transient. So this is from the inverse mode cascode, and this one is from the conventional forward mode only cascode. If you compare the color between these two raster scans, we see that much reduced peak magnitude from the inverse forward cascode configuration. And if you plot the transient response in time domain, we also see the peak reduction in the inverse forward cascode case. And for bottom one, we also see the duration reduction as well. So overall, about 40% of peak reduction, about 40% of duration reduction was achieved using this proposed cascode configuration. And the same inverse mode technique could be applied to different type of circuit. And the target circuit here is the down conversion mixer. So typically low noise amplifier is small signal circuit, but mixer is a larger signal circuit. And the inverse mode transistors are used in the switching pair of a down conversion mixer. And that's more reasonable because these transistor pairs simply switch the branch current between these two transistors. So they do not overly demand the high frequency performance. And the resulting circuit is fabricated in 130 nanometer silicon germanium BiCMOS platform. And here's the performance comparison table. And the most performance parameters are comparable, but noise figure has some notable degradation in the inverse mode mixer. But because typically mixer is placed after the low noise amplifier, so from the Freese equation, we can expect the system's noise figure will not be severely degraded in comparison with the forward mode circuit. And here we also build TCAN model for simulations. So we calibrated the DC response and small signal AC and large signal AC model. So using this model, we could simulate single event effect in the mixer circuit. And first of all, because we have two transistors in the switching pair, we want to maintain enough distance to get minimized coupling, substrate coupling between these two transistors, which was about 5 micrometer away. And the bottom figure shows when the single event effect happens in the input transistor. So in this case, the transient at the output terminal is much less when you apply the inverse mode silicon germanium HETs. And this figure shows the base and the substrate current. So when the laser strikes the bottom transistor, large portion of the excess carriers will flow out through this base terminal. As you see, much larger current, much larger base current of Q2 and Q3. So that's why you see reduced transient at the output. And when the single event effect happens at Q2 transistor, we also see the reduction in transient peak and duration, similar to the LNA case. And this is the actual laser experiment result. So there's a slight discrepancy between the simulation and the measurement result, but In general, the silicon inverse mode technique improves the transient duration and peak reduction. And these results are from the DC conditions, so no AC signals were applied. But if you apply the large LO signal, which is the normal operation condition, and we see that the inverse mode based down conversion mixer has much shorter recovery time in comparison with the normal order mode mixer circuit. So we could conclude that the inverse mode technique could be a viable approach for the mitigation of single event effects for both large and small signal circuits. And here I want to talk about the impact of technology scaling of the silicon germanium technology. So for different technology generations, I simulated the current gain and cutoff frequency and noisy figure of the inverse mode operation. So as you see, the current gain improves and cutoff frequency also increases, and the noise figure, the minimum noise figure, is decreasing as technology scales. So if we use advanced technology generation, we can apply to broader circuit or broader amplifier stage with the inverse mode silicon germanium HDTs. So if you remember the previous slides, we applied inverse mode technique to the upper transistor, but with the more advanced technology generation, you can actually use the inverse mode technique to the bottom transistor or common emitter transistor. So here we use full inverse mode based for the LNA circuit, and here's the chip micrograph, and which is fabricated in GlobalFoundries 90 nanometer technology. So for three different types of cascode configuration, we have raster scans here. So for typical forward mode only case is on the left, and this is the hybrid type cascode, and this is fully inverse mode based cascode LNA. So as you compare the colors for these three raster scan, the inverse mode only LNA shows the minimized or smallest transient peak in comparison with the other configurations. And here's the time domain comparison of the transient with of three LNAs. So as expected, the inverse mode only LNA shows minimized transient, and this is when the laser strikes the bottom transistor, and when the laser strikes the upper transistor, we still see the peak reduction. And here we summarize the performance of different types of LNAs. So for forward mode only case, it has the best RF performance, but its transient response was the worst. But if we use the inverse mode technique for both transistors, as shown here, then we still get reasonable or acceptable performance for gain and noise figure, and we can get the reduced transient response. And if we compare this performance with the forward mode only LNA using one order technology generation, and we see that performance numbers are quite comparable. So as technology scales more, then we see better performance using the fully inverse mode based circuits. Okay, and here I want to talk about the PMP, silicon germanium HDT based circuit. So in a complementary silicon germanium platform, you have both NPN and PMP transistors. And because PMP transistors have an isolation or well layer, its transient response has much less sensitivity in comparison with the NMOS counterpart. So in performance matched PM silicon germanium, complementary silicon germanium technology, we can build circuits using PNP transistors. And here is the comparison result of transient from PNP and NPN transistor, and we see reduced transient peak. So we can build circuits or high frequency circuits using PNP transistors. So in this work, we build a radio frequency switch, and in this case, we used a Germany IHP 250 nanometer complementary technology platform. And their FT and Fmax numbers are here, so it's somewhat performance matched transistors. And if you use PNP transistors for RF switch, we see about 0.6 dB increase in insertion loss, as you see in this figure, but it's still acceptable depending on the system's requirement, and we can get better single event effect sensitivity. So we conducted the laser experiment, and as expected, we have better transient waveform from the PNP version of the circuit. And if we apply the inverse mode configuration, then we get smaller transient peak. So in this case, we have two PNP transient response, but if we apply the inverse mode technique along with the PNP transistors, we get smaller transient peak and smaller charge collection. So here's the performance summary table. So insertion loss wise, we get 0.6 dB degradation, but we get much better single event transient peak and duration in comparison with the NMOS based RF switch. And the next one is about the optimization of device profile. So in this work, we modified the germanium profile, germanium doping profile, and the emitter and collector doping to optimize the performance of inverse mode operation and the single event effect sensitivity. So this is typical figure. So for forward mode, you have better FT and Fmax. For inverse mode, you have reduced FT and Fmax. And in order to improve the RF performance of the inverse mode operation, we modify the germanium doping profile, which is green color here. So in typical case, the dotted green line is the optimized germanium profile for forward mode operation. But if you can modify the profile something like box shape profile, then we can get better RF performance for the inverse mode with slight degradation of the forward mode performance. So we designed two different types of profile variants. So IM1 just used a box-like germanium profile, and IM2 used the same box profile, and it modifies emitter and collector doping. So if you see this figure, the IM1, the red, and IM2 shows improved current gain or beta of the inverse mode operation. You can ignore these two, which is not relevant to our seminar. And the corresponding transient, we get better transistor performance, but we see increased sensitivity to single event effect. So for reference, from the reference device, we got this black line transient. But if we modify the profile, then we get red curve. And if we modify the emitter and collector doping as well, then you get slightly worse transient response. So it depends on the system requirement. So if this degradation is acceptable, then we can use the modified profile, or we can adjust the emitter and collector doping for your balanced performance of your circuit. And the next topic is about the another approach to mitigate the single event effect, which is the EST structure. So you're probably familiar with the EST, electrostatic discharge. So to protect your circuit from this electrostatic discharge, we typically place corresponding circuits to sink the external pulses and while protecting your circuit. But this kind of pulse has some similar electrical signatures to single event effect as well. So we want to modify this widely used EST protection circuitry to minimize single event effect. So here's the transistor level EST-based single event effect protection circuits. So here we consider all the possible case. So your internal circuit may generate positive single event transient, or it could generate negative single event transient. To sync both cases, we have provided all the syncing paths when you have negative single event transient, and this diode path will be turned on and it will sync the transient to ground voltage level. So as a DUT, we used a RF switch in the Global Foundry 130 nanometer technology, and with and without the EST protection circuit, we see no performance differences, which means we can use this approach for any type of circuits without worrying the performance degradation as we saw in the inverse mode based technique. And this is the experiment result using pulsed laser technique. And when the laser strike the series transistor in the RF switch, we see about 80% of peak reduction in the VDD ESD current, and about 80% in peak reduction for the RF out current. And if we apply the AC signal to the switch, we still see significant peak reduction using the EST-based single event transient protection circuits. So that could be used for other circuits as well. And the next topic is about the total ionizing dose. I'll talk about the ELDRS effect. And ELDRS simply means the enhanced low dose rate sensitivity. So when you test your circuits for certain amount of dose, there may be different setup. You want to conduct your test very fast using high dose rate, or you can wait for longer using low dose rate. Ideally, both cases generate the same degradation result, but they're not always the same. So we call the ELDRS to differentiate the low dose rate sensitivity from the high dose rate sensitivity. So in order to validate, we do not have significant ELDRS effect in the silicon germanium technology. We conduct two separate experiments using very low dose rate and high dose. So this is a typical device cross-section and the result from high dose rate. And in these two cases, we applied low dose and high dose. So as you see from this figure, we saw some differences in the very low bias region, but when you design circuits using silicon germanium bipolar transistor, your bias point typically will be around zero point 0.7 or zero point 0.8 volt, which means the difference between low dose rate and high dose rate is almost negligible in these typically used regions. So, which means we can use high dose rate total ionizing dose setup without worrying about the ELDRS effect in your device. So this is about the ELDRS effect. And we conducted a similar experiment using a bandgap reference circuit. So it has some bipolar transistors and MOSFET transistor all together, but if we irradiate the entire circuit, the changes between low dose rate and high dose rate in the output voltage or bias current is almost negligible. So we don't need to worry about errors when you use silicon germanium BiCMOS technology. And the next topic is about cryogenic operation. So in extreme environment, we need to worry about very low temperature operation, which is cryogenic operation. And in this work, our duty was the inverse mode based low noise amplifier. So by using liquid nitrogen, we cool down to 77 Kelvin, and we measure the performance parameters of an LNA, such as gain, peak S21, and the noise figure. So for the mode only case, we see monotonic increase when you cool down the ambient temperature. But for inverse mode based circuits, we see some gain reduction at lower temperatures. And you can ignore the inverse mode only case because I haven't covered that detail. But for inverse forward cascade LNA, the noise figures is monotonically decreasing when cool down the ambient temperature. So we want to analyze why this gain reduction happens in this hybrid type low noise amplifier. Okay, so this is another performance summary figure. So gain comparison between these two types. And we also compare the linearity. So as gain drops at 78 Kelvin, so linearity increases at this temperature as well. So if we analyze the device level operation, we see some differences in the gamma plot or collector current plots. So this is from the forward mode transistor, and this is inverse mode transistor. And in this region, you see the slope of collector current is somewhat smaller than the forward mode case. And that means the transistor enters into high injection region much faster than the forward mode case. And as temperature goes down, the the resistance between the base collector region also increases, and that gives us unwanted internal negative feedback in the device operation, which limits the available gain of the circuits. Here's the measured result of unity gain frequency, and as you see, with lower temperatures, the FT actually decreases for the inverse mode operation. So this could be a potential weakness of using inverse mode transistor at very low temperature condition. So let me briefly introduce my current research. So the first topic is about the compact modeling of TID effects. So for advanced CMOS transistor, the dominant damaging mechanism happens in the shallow trench isolation area. So if you add some traps to STI region, and the resulting curves is somewhat similar to the measurement result. But using TCAD tools take significant amount of time. So I'm developing the compact model for SPICE simulation. So by using SPICE model, SPICE implemented PID effect, we can rapidly predict the performance degradation of transistor or circuits with reasonable accuracy. The similar work is being done for the single event effect. So for accurate result, we need to use TCAD tools like Centaurus or Silvaco. But if we have a compact model for faster simulation, that will be a lot helpful for designers to assess their circuit's performance under the extreme environment operation. In addition to that, we need to include the impact of load impedance in the compact model. So the output transient actually affected by the load impedance. So when the load becomes very large or small, the actual output transient could be very different. So the final model should consider the impact of the impedance. And regarding the electrostatic discharge-based protection circuit, we studied for the DC ESD protection circuits only. But for high-frequency input and output terminals, we need some sort of ESD structures, which is typically choke inductor, which is very large inductance. And that could provide some kind of sinking path for the transient. So we expect we get better transient response using the RF-ESD. And we also worked on the radiation-hardened transceiver design. We already designed some component circuits for the phase array system blocks. But here we haven't applied any radiation hardening techniques for their use in, for example, satellite or space-based application. We need to incorporate radiation hardening approaches for better circuit's reliability. So our previous existing circuits frequency range is 2 to 20 gigahertz, which covers major space communication protocol. So our goal is to add some sort of single event effect mitigation circuitries into these circuits. So this is a sample measurement of our power divider circuit. So the present circuit has flat response for all the entire frequency range. Okay, so here's my summary. So today I gave you some introduction to extreme environment electronics. For designing this type of circuits, we need to think about how we can handle radiation effect in the design phase. So I talked about two main mechanisms. One is the single event effect, which is the dynamic interferences from the collision with high energy particle. In order to mitigate the single event effect, I introduced inverse mode silicon germanium HDP and ESD-based structures and PMP bipolar transistor. Also, we can think about the profile optimization for balanced performance and SED sensitivity. For TID, total ionizing dose effect, I showed we don't need to worry about low dose rate or high dose rate as long as you use silicon germanium by CMOS technology. And I showed the cryogenic operation of the inverse mode based amplifier, and we saw some potential issues of gain reduction at very low temperature, so that has to be solved for future design. And my current research includes some sort of compact modeling of total ionizing dose or single event effects. And we are also working on the modified ESD structures for high frequency terminals. And at the same time, we are working on the applying radiation hardening techniques to high frequency transceivers. So that's all I have for today. Thank you very much for your attention.
네, 발표 잘 해주셔서 감사드리고요. 혹시 들으시는 분들 중에 질문 있으신 분 있으면 해주시기 바랍니다.
예, 송 교수님 발표 잘 들었고요. 오래간만에 바이플라 트랜지스터 오래간만에 보는 것 같네요.
네.
아까 말씀하신 것 중에 인버스 모드로 할 때 전류가 이렇게 높은 VD에서 디그레데이션 되는 게 혹시 에미터 저항 영향이 더 큰 거 아닌가요? 컬렉터 저쪽에 도핑이 낮아가지고 에미터가 될 텐데 인젝션이 하이 인젝션 되기 어려울 것 같은데 그냥 예, 제가 궁금해서 질문 드려봤습니다. 예. 에미터 저항 영향이 크지 않나요? 그때는 이제 컬렉터가 에미터 되니까.
예, 그럴 수도 있습니다. 제가 지금 사실은 이제 티켓의 모델 좀 만들어서 분석을 하려고 하는데, 약간은 이게 온도가 내려갈수록 이 컨버전스가 좀 잡는 게 어려워서요. 그거를 이제 어떤 수치상으로 좀 완벽히 분석을 해보지는 못했습니다. 근데 말씀하신 대로, 에미터 쪽 영향도 있을 것 같고, 그리고, 여기 아까, 그쪽을 말씀하시는 건지.
네네네. 아까 말씀하실 때.
네.
예.
그래서 이 스노비 눕는 게 하이 인젝션이 좀 일단은 발생을 하는 영역으로 들어갈 것 같고요. 그리고, 이미터 쪽 저항도 영향을 주긴 할 것 같습니다. 근데 저희가 이제 그거를 완벽하게 분석을 하지는 못해서 뭐 조금 더 이제 모델을 가다듬어 가지고 예, 좀 정량적으로 분석을 해볼 계획입니다.
예, 감사합니다.
네.
네, 저도 질문 한 가지 있는데요. 사실 저는 그러니까 이쪽 분야를 잘 몰라서 그냥 하이 레벨에서 제일 처음에 인트로덕션 설명하시면서 말씀해 주셨던 것 중에 그러니까 말씀하신 대로 사실 디지털 회로들 같은 경우는 뭔가 알고리즘 레벨에서 에러 커렉션 할 수 있는 그런 애들이 그럴 수 있는 요구수가 많이 있을 것 같은데 말씀하신 대로 아날로그 회로는 그런 게 되게 어려울 것 같다는 생각이 들었는데요. 근데 그러면은 지금 현재는 어떻게 이거를 해결을 하고 있는 건가요?
그러니까 현재에서 가장 할 수 있는 좋은 방법은, 어, 최대한 두꺼운 쉴드를 사용해서 납이라든가 그런 메탈의 어떤 벌키한 메탈을 사용해서 최대한 레디에이션 임팩트를 막는 수준으로는 하고 있습니다. 근데 이제 예를 들어 큐브셋이라든지 우리가 뭔가 인공위성을 같이 뭐 인공위성 네트워크 같은 걸 만든다고 할 때 이제 그런 무게나 부피가 커지는 거에 대한 영향성이 점점 이제 벌든으로 다가오기 때문에 그거를 이제 줄이려면 우리가 뭔가 설계 단계에서도 조금 아이디어를 내서 그거를 이제 좀 덜 쓰거나 아니면 안 쓸 수 있는 수준으로 만들어야 좀 더 경제성 있는 그런 시스템을 개발할 수 있을 거라고 생각을 합니다. 그래서 이제 그런 관점에서 이제 좀 디자인이나 어떤 디바이스의 동작을 좀 잘 분석을 해서 어떻게 그거를 완화할 수 있을까? 그러니까 특별히 레디에이션 하든드 뭐 디바이스를 사용하지 않고 어떤 그런 스페셜한 프로텍션 스트럭처를 사용하지 않고 그냥 우리가 쉽게 사용할 수 있는 테크놀로지를 사용했을 때 어느 정도 개선까지 얻을 수 있는지. 그래서 그게 억셉터블한 수준까지 간다면 굳이 우리가 좀 뭐 무게가 많이 나가고 부피가 큰 그런 어떤 스트럭처들을 좀 사용하지 않을 수 있지 않을까 그런 목표를 가지고 연구를 했습니다.
알겠습니다. 혹시 다른 분들 중에 질문 있으신 분 있나요? 네, 특별히 없으시면 송희경 교수님 다시 한번 저희 행사에 응해 주셔서 감사드리고요. 네, 나중에 실제로 뵙고 정식으로 인사드릴 수 있으면 좋겠네요. 네, 제가 그 행사 다 끝나고 다시 한번 이메일로 그 연락 한번 드리도록 하겠습니다.
네, 감사합니다.
감사드립니다.
네, 좋은 하루 되십시오.
네, 수고했습니다.
네.